Welcome back to the lab. Today we're going to talk about buck converters, tuning the peak current limit of our NCP3020 based supply, and why we designed a buck based on the LMR 14050. First things first, let's talk about what happened while tuning the peak current limit. If you've been following along, this journey all started with some old FETs where we were riding things a little bit too close to the safe operating area limit. Yeah, we blew up a few FETs. Maybe more than a few, maybe more like 20 FETs. Eventually, through all of these failures, we eventually got to a place where we understood the failure and we knew how to move forward. And what I mean by that is that we needed to get a FET with a higher safe operating area limit, like a higher absolute limit for the peak power that these transistors can absorb. It's how we're going to prevent this thing from blowing itself up, right? Well, maybe. So I got some FETs on order and we started tweaking that peak current limit. With the old FETs, we could get around an amp. We could set the peak current limit to about an amp, and that would not give us very much output power at all, but at least it would keep the transistors alive. And we saw a short circuit would lead to a hiccup recovery mode and everything was hunky-dory. It was great. We were ready to move forward. So, grabbed a new FET, put it in the design, got our peak current limit trimmed to around 3 amps, which was the only place that we could get it set with the resistors we have on hand. So not really ideal, but it worked for a while. See, I walked away, I came back, turned it on, and then a power supply blew up. What? That's not supposed to happen. We had this thing fault tolerant just that morning, left, came back, and now it exploded. No, this is unacceptable. I have no idea what went wrong because I investigated and both of those transistors were fine. We didn't violate the safe operating area of either of those parts. The controller just died. What? Yeah, this was just a failure in the low side gate driver, and I have no explanation. It's not the high side driver, it's the low side one, and it just randomly shorts itself to ground and takes the rest of the controller with it. The NCP3020s are just dying. So I investigated a little further. I looked into a dev board, see, hey, maybe there's a reference design from On Semi. Maybe this will explain a little bit about how we implemented this poorly. Maybe there was a gotcha or a trap for young players that we fell into. But I couldn't find anything. The NCP3020 is clearly rated to operate up to 28 volts in. That makes sense. The interesting thing is that on their evaluation board from On Semiconductor, the evaluation board for the NCP3020, they limit the maximum input voltage range to 18. They limited the maximum input voltage range to 18 volts, and that sounds a little fishy, right? Why would you limit the input voltage of a dev board for a buck converter to 10 volts less than the maximum rated input voltage? I think this could be a mitigation for the fact that their part just blows itself to pieces sometimes. It might have just been designed to operate with more design margin, which is bizarre. When I buy a part rated for 28 volts, I would expect it to work at 28 volts. Now, 4 volts of margin isn't a lot. Maybe I should have given it a little more, but still. Digging in a little further, I think the issue might be something related with the bootstrap capacitor. Like maybe there isn't an internal Zener diode that clamps the 15 volt above the source voltage, and that's what we're running into. Like we're exceeding some peak voltage rating inside the part because we're bootstrapping to 24 volts above 24 volts, and that might be causing something to break down. But long story short, I've completely lost faith in this controller. If it's designed to operate above the regular operating voltage of a FET, I would expect it to have an internal method of regulating that voltage down to something that's not going to cause things to explode. I've made the control loop stable. The transient response is good. This thing's pretty well optimized. The efficiency is acceptable. And I don't want to fart around the rest of it. I just want it to work. That's why we're using a switch mode power supply controller with an integrated gate drive. So it just works. It just makes me angry. It makes me so angry when we do the analysis and the difficult things are optimized well and the easy things just let out a massive fart. Moving forward, I want to be a little transparent here, and I'm being a little cost conscious. I'm being pretty cost conscious in this design. I know that every part that I put on this board, every part I put into this design is a part that will need to get paid for. That's a part that's going to need to get placed as well. And the NCP3020 design, not only does it add this technical risk because I'm losing faith in the datasheet and the ratings of the part, it's also got a lot of components in the design. After searching for more tightly integrated solutions, something that leads to less components on the board, after doing a little bit of soul searching, I found some tightly integrated solutions. I found that controllers with integrated gate drive implementations for controllers at the bottom of the bucket when it comes to price, well, they're just not the best. See, I'd typically like to see a description of, for example, how a controller implements dead time. Right? Maybe it's using diode emulation, maybe it's using fixed dead time that you program with a resistor. There's lots of different ways to do it, but the datasheets weren't saying anything about it at all. They weren't giving me the information that I would need to build confidence in the overall design. And so basically I wasn't finding a controller that would convince me that it wasn't going to blast both of my transistors into another dimension. So I wasn't a fan. Once I climbed up to a position where the controllers were describing their operation well, we were at about $7 for the controller in small quantities. Nah, that was too much. I set my pride aside and I started looking at other options, being open to giving up synchronous rectification. Eventually, this is where we found ourselves with the LMR 14050. This is a switch-mode power supply regulator rated for operation up to 40 volts, contains an integrated high-side transistor as well as the gate driver. This allows for the same type of lossless current sensing, but also for internal temperature compensation. Booyah! Throw an external rectifier diode on there and we'll be moving along in no time at all. Perfect. While I was making these design changes, I selected a higher voltage rated MLCC for the input capacitance and reduced the amount of electrolytic caps used in the design, removed the series PTC, a couple improvements to compensate for the lower efficiency of the core converter to keep the total system efficiency the same. Now we had a choice, right? We made a pretty critical change. We've now redesigned the 5 volt, 15 and 12 volt buck converter. These are connected to every other subcircuit, which is the reason why we had to call an audible last week and do the 5 volt circuits instead of moving forward with these power converters. So what would we like to do? Would we like to do a total redo? Should we just throw away our dev board and order a new massive board? Or should we make a little buck converter module? Well, I was thinking about this for a little while and I eventually decided to make the small board. So this will mean that we'll have 3 small modules strapped on top of our Proto board. And why would I do this, might you ask? Well, I just laid out the little board to see what would happen, and turns out it would only cost $6 for 20 of those PCBs, and some parts are on the way. What this eventually leads to is that if the design works well and we don't blow up many parts, we could build 5, 10, 15, maybe even 20 of these power supplies and just have some general purpose buck converters on hand. That could be pretty handy, right? We know how this design works, we know its limits well, we know that it should be able to output about 5 amps of current, so this has a wide input voltage range up to 40 volts and an output voltage range up to 24. Should be pretty useful as a general bit of kit around the shop, and I figured, hey, maybe there's a couple people in our community that wouldn't mind receiving a buck converter, so thank you for doing something awesome. Maybe we'll have some kind of design contest, maybe we'll, I don't know. Let me know what you'd be interested in, what would get you excited and working on some projects at home. I want to encourage you guys to be working on these projects, so we can throw in a little something like a couple homegrown buck converter kits, or I don't know, maybe even, a current source kit? Electronic load? Yep, we've got some ideas. So just let me know what you'd be interested in. Moving on from there, I just want to take a moment to appreciate the 3D viewer in KiCad. I think this is a pretty awesome tool. I know it's not perfect, but as far as free EDA tools, man, I love KiCad. Definitely check it out if you haven't before. The DRCs and the method of making components is totally worth it in my opinion. Even though it was painful, I believe that moving to a diode rectified topology is going to result in a more reliable converter for the same price as our previous implementation. With parts and board in the mail, I can't wait to revisit this next weekend. I can't wait to revisit testing the buck converters in depth so we can finally get through the line regulation, load regulation, efficiency, burn-in testing, transient response, and so much more. If you like what you saw today, consider subscribing to be notified of our future videos where we will talk about the accident waiting to happen that we got from Amazon. It's our new soldering station. Sure, we'll call it a soldering station. And we're going to test the isolation amplifier that we're going to use to monitor mains voltage. If you want to support the channel, consider checking out the products that we featured today through our Amazon affiliate links in the description. It really helps us out a lot. Thank you. I think that the new buck converter design is great. TI controllers for the win, yo! If you like the LMR 14050, even though we had to give up synchronous rectification, or you have your own favorite 6-point power supply controller vendor and you want to let us know about it, hit that like button on the video, leave a comment letting us know what's on your mind. Most of all, I hope that you learned something great today, and I hope to see you again soon. So thanks for watching EEforEveryone, and thank you for staying till the end. Bye!